So now let me introduce the first session. So the first session on common sense reasoning is going to be chaired by Sri Narayanan, who's a professor of electrical engineering and computer science and also a director here at the Information Sciences Institute. So Sri, I'm going to turn it over to you now.
Thank you so much, Craig, and welcome everyone to our third edition of our series in AI that we've been hosting at USC. So the first session on common sense reasoning has four talks, and they are fairly sort of, fast-paced, 8 minutes as a reminder to our speakers. And I would request our audience and others to put their questions in the Q&A or chat session so we could handle the questions at the end of the session. So without further ado, I would like to introduce the first speaker, Philip Ilievsky. As you heard, that he was instrumental in organizing the session as well. Thank you, Philip. And the first talk is, Philip is a research scientist at the Information Sciences Institute. And the first talk is entitled Open World Agents. Philip, on to you.
Thank you, Sri, and Craig for the introduction, and welcome everybody. So the first talk is on the topic of open world agents. When we talk about the future, when we talk about the future of our society, very often we envision that, you know, in 20, 30 years, we'll have AI agents that do very complicated things. You know, they help us in our households, they clean for us, they navigate complex information, they can anticipate, you know, complex situations like in traffic, intentions of other drivers. Maybe they can even entertain us, as shown in bottom right. However, next slide, we keep finding that one of the key obstacles towards getting to this future vision is the lack of common sense. So on one hand, we have AI that sometimes can do very impressive things, but at the same time, we have AI that can make these silly mistakes. Like here we have Oren and Zioni from AI2 presenting, showing this example where a computer vision system thinks that this bubble behind the duck is actually a car, which is not only wrong, but it's also just non-commonsensical somehow for people. Next slide. So common sense, as Craig pointed out, has been a topic that has been with AI since the beginning, since you know, the 50s. And here are two definitions that I think that I'm going to use to ground this a little bit. So one is by Ernest Davis, who is one of the prominent researchers in this field, that says, you know, common sense is the common knowledge about the world that is possessed by every school child and the methods for making obvious inferences from this knowledge. And then the obvious question is, well, what knowledge are we actually talking about here? And common sense knowledge, according to John McCarthy, includes the basic facts about events and their effects, facts about knowledge and how it's obtained, facts about beliefs and desires, and as well as facts about material objects and their properties. So this is quite a wide set of knowledge aspects that is covered in here. Next slide. Specifically, when we talk about common sense, usually we talk about these three different pillars. So there is the pillar of intuitive physics, there is the pillar of common sense psychology or naive psychology, and then there is the part on common facts. In the bottom here, I included some of the pioneer literature in all of these, some of the very prominent literature. One of, like, the fourth book is the one, the work on common sense psychology. Is actually some of the key work has been done by Andrew Gordon and Jerry Hobbs, who are actually USC researchers. And you know, Ken Forbes, who is the author of the third book, will be one of the panelists tomorrow. So, you know, I think we will cover some of this during this symposium. Okay, so going to the research goal that I would like to bring up here is, you know, so we have all these wide aspects of knowledge, and we want to have AI that can deal with them. So the research goal is naturally how to build a natural language agent that can perform well on all known aspects of common sense. And the way in which this is done in practice today, next slide, please, is we have something like that with the language models, except that we tend to build one AI agent per data set. So we have data sets or benchmarks that are being created, and then what happens in practice is that we instantiate one agent per data set, and then it's unclear how much can they generalize. Instead, next slide, what we would like to do is we would like to have a single common sense agent that can perform well on a bunch of tasks that it will encounter, and also be able to transfer knowledge from one task to another without needing to rely on the training data for these tasks. So I'll talk about a few works that we've done towards this goal. The first one is, so we started by looking at the knowledge that is out there. So our idea was to actually take language models and see how we can teach them to understand common sense better. And we found that there is a lot of common sense knowledge out there, except that this common sense knowledge is very dispersed, and it's also very heterogeneous. So using this knowledge together proved to be a big obstacle. So the first thing that we did is we created CSKG, the Common Sense Knowledge Graph, which integrates 7 different sources of common sense knowledge. Probably you've heard about most of these, Atomic, ConceptNet, FrameNet, WordNet, Visual Genome, Wikidata, and Rosette. So we created this into one common sense knowledge graph so we can use this in language models in order to improve their generalizability. Next slide. So then we devised a method. The method is basically using this common sense knowledge graph to create artificial questions, many of them millions, in order to teach a language model to perform better on common sense tasks. And here in this paper published at AAAI this year, we show that across different common sense tasks, we can get somewhere between 5 and 20% improvement. Next slide, please. Now that we have consolidated the knowledge into a single graph, the next thing we can do is we can look into organizing the knowledge into different dimensions. So in this follow-up work, Dimensions of Common Sense Knowledge, we devised 13 different dimensions that we can use to basically cluster the knowledge in the common sense knowledge graph. And then we showed that some of these are more useful than others for common sense reasoning on different tasks. So we saw that, for example, temporal reasoning and utility reasoning, this kind of knowledge is very useful for language models to learn from, whereas, for example, lexical knowledge or taxonomic knowledge is less. So this shows that by consolidating knowledge, we have this additional benefit of being able to use the structure of the knowledge to further make a choice. Next slide, please. So I'll just like to point 2 more works. So here, what we did is we show that this common sense knowledge can help for a bunch of data sets, but it especially can help on out of domain data reasoning, which has been shown to repeatedly be a big challenge. Next slide. And in the ongoing work, we are trying to integrate this common sense knowledge graph with the psychological axioms that have been devised by our own Gordon and Hobbs. And here is one ongoing work where we generate many stories, hundreds of thousands of stories, by combining the common sense knowledge graph with axioms, and doing some extraction around that. Next slide. So to conclude, the story so far has been that the mission has been, my mission has been to create open world agents with common sense, and we started by the large language models, which are very, very powerful. They have they have the power to generalize over tasks, but they lack common sense. So in order to improve this, we devised a method for generalizable zero-shot pre-training. And then we took the common sense knowledge, we performed the consolidation of this knowledge, we organized the knowledge into different dimensions, and currently we are working on axiomatizing, so adding more rules and more structured knowledge on top of this. Thank you for your attention.
Thank you, Philip. So we will move on to our next speaker. Please hold your questions and put them in the Q&A for discussion at the end. We'll go on to our next speaker in today's session. The next speaker is Manuel Chiosicci. Manuel is a postdoctoral researcher at the Information Sciences Institute here at Viterbi School of Engineering, and his talk is entitled Predicting Events. Manuel?
Thank you. Next slide. So I want to ask you to imagine a future where AI agents had access to vast repositories of step-by-step knowledge that they understood and that they could then use to guide us through long and complicated processes. Think of something like buying a house, which is a very complex process with many actors and many steps. But before we get there, we must first create a library of this script knowledge. Next slide. So to do that, we've been working at ISI and Malta on a web tool we call machine-assisted script curation that we've also published and presented at NACL this year. It's a web-based tool that assists humans in the creation of a repository of scripts that describe multi-actor event sequences. But we've also tried to automate this process by adding assistance for adding event types and event arguments or actors, and suggesting automatic steps. And this is the part I want to focus on in this talk today, discussing the automatic step generation. So on the right side of the slide, I have a script for buying a car that starts with what everyone would expect, like identifying your needs and your wants and your future needs, and then a budget, and then continues through the process of figuring out what the best car is for you, up to ending with the last step, which is the actual purchase of the car. Next step. So in automatic step generation, we started focusing on pre-trained language models because we've seen recently that zero-shot natural language performance, natural language processing performance is very good for these models, and that hints at there being knowledge stored in these language models. We've also seen that the GPT family of language models can generate short text that is logically consistent, and these are two elements that we want to take advantage of. So in our system, next slide, we've implemented two ways of helping humans by generating steps. The first one is what we call batch step generation. What we do here is that we take a GPT model off the shelf, so we're not fine-tuning or pre-training in any way, and use it to assist a human in the creation of a script. So a human first adds events to a script, and then a temporal order, saves a script, and then later a GPT model comes, and we first take the graph of events, turn it into an event sequence, have the model try to predict what the next event is in that sequence, and then we filter those generations so that we remove duplicates, so things that the human has already added in the script, and also occasional profanity. GPT occasionally likes to swear. And then we come back with these suggestions to the human and allow the human to accept or reject generations. Next slide. So here you have, in the top image, you have our buying a car script again that the human entered, so identify our needs, wants, and so on. And then we can see generations coming from GPT. Next slide. So after identifying your future needs, for example, GPT says, maybe evaluate the financial implications of a purchase. After you decide on your budget, GPT says, well, maybe consider financing, or maybe make a list of your options. So at this point, the human can accept or ignore those suggestions. In a different mode that we call mixed initiative, we're also using a GPT model off the shelf. Here we want to make the script generation process a little easier on the human. So instead of a human creating a script and then having the computer come back later and add to the script, we allow human and a computer to work interactively. So humans start by defining the script name that they want to work on, and then maybe a definition. So say buying a car and what buying a car is. And then the language model immediately comes up with 5 suggestions for what a first step might be. Then the human can either accept one of the suggestions, take one down and adjust it to fit their need, or ignore all of the suggestions and write a completely new step. As soon as a step is added to the script, whether that's manually entered or one of the suggestions, GPT then uses, again, all the information it has, so the script name, description, and then all the steps that are already in the script to come up with new suggestions. And on the right side, you can see what happens in this mode if one starts a script for purchasing a car, from identifying your needs, wants, and future needs, and then GPT comes up with suggestions like, check the price or make a list of the features you want or select the car. Next slide. So in looking at this, these two ways of adding to scripts by using automated event prediction, we have to also discuss quality. And the way we discuss quality is in terms of acceptability. So how many of these generations that come from a language model humans like and would like to see in their scripts. So for batch suggestion, we had a person generate 5 scripts. And then we allowed GPT-2 to go through the scripts and figure out where the model would like to add events. And we've seen that when we asked the same author to look at the generations again, in 4 out of the 5 scripts, they found events that GPT had generated that were not in the original script, that made sense, and that should have been in the original script. For mixed initiative, we had multiple people create 12 sample scripts, and we've seen that roughly half of the times GPT suggests a step, the humans accept one of the suggestions there. So that shows us roughly about how practical this approach is. We've also done other experiments where we've looked at domain-specific event generation for improvised explosive devices or for disease spread, where we've manually evaluated with a 3-point Likert scale, and we noticed that larger models tend to generate better suggestions. We've also noticed that if once one specializes the domain, having domain-specific pre-training, so allowing the model to go and read news items from, say, disease spread, improves the quality of those suggestions. We've also noticed that if the domain gets specialized, like for disease spread, the model occasionally has issues generating correct domain-specific knowledge. So it occasionally messes up the biology of say, how specific diseases work or what medical treatments make sense. Next slide. In terms of temporal order, we currently have a rather simple approach to looking at events. For both of the modes, so for both batch suggestion and for mixed initiative, we assume that steps follow each other in a sequence. So, B comes after A, C comes after B. And in both modes, we allow a human to have the final decision on what gets added to a script and what is considered to be relevant for that particular script. Of course, there's some limitations in how we treat temporal order. The first one is that we always work with sequences and we always insert at the end of a sequence. So if a script contains event A, we could generate an event B. If a script contained A or C, we can either take A and hope to generate B, or we can take A and C and hope to generate D. We also don't have any granularity control, so we could have GPT jump all the way to the end of a script and generate event Z instead of giving us event B. We also cannot generate alternatives, so we can't tell the language model, this is one way this process can unfold, now give me another way that this process can unfold. Next slide. We're also looking into ways to improve the generation. One way to do that is to fine-tune the model on scripts. We're slowly building a library of scripts that will be useful for training GPT so that it understands what an event is and what event granularity is and what we're looking for. We're also looking at having the model read a bunch of different disease books on history of diseases and transmissibility and epidemiology to get a better domain understanding. And lastly, we're looking at helping human curators even more by instead of coming back after they do the work and suggest things they've missed, or working together with them in real time and suggest next steps, to come up with short scripts of say 4 to 5 events that the human can take and immediately edit or work with so that we make their work even easier. That's it for me for today. Thank you.
Thank you so much, Manuel. As always, I request any questions for Manuel in the Q&A, and we'll address them at the end of the session. Moving on to our next speaker. Our next speaker is Ram Navatia, the Fletcher Jones Professor of Computer Science and Electrical and Computer Engineering at our Viterbi School of Engineering. He's a very pioneering researcher in AI, and his talk is going to be on visual grounding. Ram, please take it on.
Hi, thank you very much. I have to start with a confession that I completely miscalculated the allowed time for this talk, so I prepared a 20-minute talk. I don't want to take anybody's time, so please, Sri, tell me when my time is coming up. I will try to give as much of an overview instead of details as possible. So I'll start with this slide that shows various tasks where vision and language come together. since I don't have a control of the mouse, there's the captioning in the left column that says in language what's happening. The next one is FOIL, it's some correction. Let's skip that. The one I'm going to focus on is referring expression recognition, also called grounding. That is, we specify some object that we want the machine to detect, like bird to the left of the feeder. There's visual questioning answering, there's dialogue, there are various other tasks. Not going to directly talk about them. I'm also not directly going to talk about common sense, though Philippe gave a nice introduction that the car in the lake was not making much sense. So there are lots of examples in vision. Vision systems make all kinds of silly errors, but how to bring the common sense to correct it is not clear at all. Next slide, please. So object grounding is simply localizing entities in images or videos that are given by some expression. And the entities, I'll just focus on objects, which could be characterized by their category, attributes like red car, relations, where they are, or their semantic role in an action. Probably won't get time to talk about semantic roles because of misunderstanding of time allocation. And we want to localize these objects in space and time. Common sense may help prevent many obvious errors, but not clear how we incorporate such knowledge in deep learning framework. I think Craig mentioned work like Doug Lennett's work on psych, but how do we incorporate psych-like rules in deep learning is not clear. I'll say a little bit about pitfalls in experiment design, probably comes up everywhere. VQA is visual question answering. And in many of the data sets, if you just don't look at the image at all or video at all, you can get better answers because the data sets are so biased. And in grounding, which I will talk about, often there's only one category, one instance of a category. If there's only one cat, we don't have to say cat in the left or cat looking somewhere. Next slide, please. So a basic pipeline is as shown in this block diagram. I'll speed through it. The block in green is the visual processing. The system finds some what we call proposals, boxes, where some object is likely to be present. We compute features for that. The blue box takes the phrase that we want to localize, compute some embedding for it. The vision in language vectors get concatenated or combined in some other way, and they're used to find whether that proposal actually corresponds to the phrase or not. Next slide. So here's some results. A young tennis player wearing yellow shirt, etc. Good detections are shown. This is a standard data set. I was proud of this work when we first published it in 2017, but in some sense, it's got a basic flaw that there's only one shirt there. So as long as we can find a shirt, we don't have to know that it's yellow or that there's only one person in there, so must be a tennis player. The bottom row actually does show multiple instances. There are many hats, and we need to ground the right hat. Next. We next start to look at zero-shot grounding. So on the left panel, you can see there was a red car, there was a blue shirt in our training data set. So we should be able to find blue car. This is very standard in grounding data, but we wanted to see if we could find objects that we had never seen. We had never seen, meaning that training system had never seen them. Can we find them just based on their linguistic representation? I'll give a different example than, well, yeah, a car versus minivan. Minivan has never been seen in training data. What can we say about minivan that will help the visual system find it? We could say it's a little bit larger, it's boxier, and so on, but that's not what our vision system understands. So we just take the embedding of these words and hope that the embedding alone, that the differences in linguistic embedding and visual embedding are similar enough that we can find these objects. Shri, how am I doing on time?
You have a couple of minutes, Ram.
Okay, so let me skip this slide. Our pipeline is, again, very similar to before. We get visual features, we get language features, we concatenate them. Next slide. I'll just hopefully show some examples. Carefully, we characterize the kind of new things you get. In this example, if the word is not seen before, we consider it a new category. Next. Here, the category itself is new, like chair. Not only we have not seen a chair before, we haven't seen any furniture before in our training data. Next. Here, we have a minivan. We have seen some similar objects, and it matters whether the similar object is also present in the image or not, because if only minivan is there, we find it as a car, we don't have a problem. Next. Here we have a car as well as a moped. We may be confused between the two. Next. So here's some successful and non-successful examples. Cigar, we don't know, but cigarettes, we know. Couch, we have never seen any furniture, we get it right. Countertop, we don't get right. Next. Rocky cliff, we know about a hill, but not a cliff. Shorts, planter, we get wrong, we get the plant instead of the planter, and so on. Yeah, next. Here's some numbers. I don't have time to go through the numbers, but the numbers are not anywhere near 100%. They are much, much better than what random chance would give us, and how to close the gap and how common sense reasoning could help would be a good topic. Give me the next slide, and I will conclude with that. The part of the talk I won't have time to do is if there's an action happening, like the man passes a ball to a group of kids, the various objects have semantic roles, and can we use the semantic roles to ground them? So I think I'll stop here. Yeah, maybe you can go to my conclusion slide. That visual grounding is a challenging topic. There are many hidden traps in evaluation. And even though linguistic compositionality is inherent, how do we enable zero-shot capability? Like in language, there has been a development on very large-scale learning in CLIP, and it's not clear if CLIP incorporates common sense just by having observed so much data. That may be a generic question, like, does the common sense have to be captured explicitly, or can it be implicit in what the machine learns from a vast, vast amounts of data? Okay, I think I'll stop here and we'll take questions at the end. Thank you for
Thank you so much, Ram. So to the final speaker of our this session on common sense reasoning is Professor Zhang Ren from the Computer Science Department at USC. Next slide, please. So Zhang's talk will be on explaining explaining with common sense. Zhang, please take note.
Thank you. Thanks for having me. Can you guys hear me fine? So yeah, I would like to share some of our work that trying to externalize the AI models kind of inner working with the common sense knowledge they are leveraging, and also the common sense reasoning process they are trying to make to facilitate these kind of tasks. Yeah, so I want to start with just motivating this kind of a problem a bit more. So as many of you probably encounter in your kind of research career, that like you've been working on certain NLP problems or AI problems, and at the next day you find out that actually on the leaderboards of some of these problems, they actually have really impressive results that have been published by likely huge models that have a lot of parameters. And there you can even see sometimes these like a superhuman performance on these models, and you kind of start wondering whether you should change your thesis topic because of that. Next slide, please. And that such good results also kind of probably caused other people's attention, like your friends in industry might try to really take advantage of these state-of-the-art models and trying to actually deploy them on the online services. And that's where you start seeing a lot of new problems, and the system start breaking, probably due to data distribution shift, due to the fact that lack of training data or other actually constraints or concerns from the customers of the service you deploy. Next slide. So if you try to summarize these phenomena we've seen here, I would like to argue that the most of the ways we've been seeing how the research being done and published and move forward is trying to create tasks and models that perform well on a specific benchmarks. And that means like usually you collect your data from a particular domain, and you're trying to create this like training split and evaluation or developing and test splits in a kind of usually IID manner. And that means like the sort of the model you are trying to create, refine, and polish in such a setup is usually highly customized for these narrow tasks where it's very specific properties and characteristics you're trying to create. And therefore, it is hard for them to deal with these unseen and novel situations and or struggle with handling these underspecified inputs. Next, please. And versus what we really want to achieve in this like having general AI capability is to have systems that can perform well in the wild, and that refers to having these systems that can generalize to unseen cases that are not very well present or not even present in the training set for the system, or like can be robust to perturbations that possibly have that are not present in the training set, and is like more efficient in terms of the consumptions of training data, and more importantly is becoming responsible and trustworthy, and part of that meaning being explainable for what it's actually doing and the rationales behind that. And our efforts along this line starts with actually making our predictive models for many of the NLP tasks, like multi-choice question answering, become more transparent by itself. And the way we do that is to, in addition to having this semantic space, which the current neural language models usually can do, for example, taking a question sentence like, where do adults use glue sticks? And one of the answer choice like office, the language model will just see this as a natural language text sequence and trying to create a neural embedding out of it. And that neural embedding is turned into a classifier to output a plausibility score for evaluating how likely or how plausible the given choice is with respect to the question that I ask. But other than that, our proposal here is a symbolic space that are associated with the questions that you are answering here. For example, seeing the question, we now know the key concepts involved in the question is like adults, it's a object node, and then use is an action node, glue sticks is another object node. So then we start looking around in an existing knowledge graph, for example, like ConceptNav, to see what are the connections between these concepts. So then you find out that, okay, adult is capable of working can happen at office, glue sticks can be used by a person, and glue sticks can be located at office. And all of this becoming the common sense knowledge. And the way you take into the whole graph into account for driving to the most plausible answer is the common sense reasoning process that can actually be formalized as a sort of a graph reasoning process that drives to the final answer. Next slide. And you see that we're starting with this like a relatively artificial multi-choice question answering task where the answers is actually very limited set of options that we can choose from. So we can easily turn that into a discriminated modeling task where we just choose one of the best from the remaining 5. And then we step forward to think about how can we really make this a useful common sense service. For example, just think about taking some given constraints of concepts as the input and really output natural language sentence that make common sense to human, right? So we actually try to formalize such a task where we call it like a generated common sense reasoning. As example here, you are given concept words like dog, frisbee, catch, and throw. And you are asking to compose a single sentence out of these like 4 or 5 given concept words. And the sentence not only need to be grammatically correct and fluent, but also have to be plausible to human as reflecting the daily life scene or observations they probably would see. Like, for example, a dog lives to catch a thrown frisbee is a good sentence versus like you won't see sentence like a dog throw a frisbee to human, right? So the challenge of this task is like there's actually a lot of relationships, common sense relationships between these common concepts need to be recorded by the model in order to make the reasoning. And also the system has to do generalization on unseen compositions of the concepts that are never present in the training set. Next slide, please. And when we're looking back at what are the ways people be solving this kind of problem, it's usually a pretty end-to-end data-driven way without too much transparency and explicit demonstrating of the inner working process of the model. So usually they just take pairs of concept words to sentence as a training data. They try to learn a language model in a data-driven way. And the best have been done is just to adding some additional knowledge sentences or statements that are retrieved from knowledge graph or retrieved from Wikipedia as concatenating to the concept sets to help make the language model to be more informed. And our solution here as a very kind of a aligned kind of spirits with the previous demonstration of using the symbolic space, we are trying to have an imagination module that can really externalize what is the possible relationships and the relative and the implicit concepts that are related to the given set of concepts. And we call that scene knowledge graph. And next slide, please. And with this scene knowledge graph, we'll build a verbalization module that can turn this structured graph into really a natural language sentence that are fluent. And this whole thing is interesting in the sense that the imagination module is actually a general purpose plug and play module that we are pre-trained from other resources. And we can plug in here and we can just take the same knowledge graph and the input concepts to train a customized verbalization module using the task training data. Next, please. And just to give you a little bit more idea, in our work, we've been building this imagination module using a vast amount of common sense resources of different modality. For example, image captions, stories that are collecting from video, or scene graph that are passed from the images. All of these were taken together to be used to pre-train an imagination module. And we actually apply them to multiple different data sets for generating sentences out of concepts. Next, please. And that turns out to be pretty giving pretty encouraging results. On the right-hand side, you can see the leaderboard of CommonGen, one example of this reasoning task. And we actually perform on par with the second best model, and also just like 2 points less than the first model, which the first model is 30 times bigger than our model because of the retrieval corpus they are using. So we believe there's a lot to again in the coming research to encourage our model to have a more expressive language model weights. And the left-hand side just shows you that the imagination module does bring more reasonable sentence rather than giving you a sentence like a dog is throwing things to its owner because of the scene graph that I imagined given the concepts. And that concludes my talk about like how to externalize common sense, knowledge, and reasoning for helping expanding AI model and making it more generalizable. Thank you.
Many thanks, Zhang, and many thanks to all the speakers, Philip, Manuel, Ram, and Zhang for your talks. Now, we have some time for questions for all the speakers in this session. I have a couple of questions already posted in the Q&A. I asked our audience to post it in the Q&A so I could read it so it'd be easy to coordinate it. So the first question is from Patrick Stingley. It's actually directed to both Philip and to Manuel. I'll ask Philip to take it first. It says, what's a story? How is it serialized?
Right. Thank you, Patrick, for your question. So I think for our purpose, I think we see stories as a sequence of events that are connected somehow with a purpose. And we are sort of inspired by other tasks like rock stories, where you have which is a story completion task where you have 4 sentences and you have to say which of the 2 alternatives, for example, are possible, are the right ending. I think the catch about stories is that is the keyword purpose, right? So I think, and that's also why we think that you can't really generate stories solely by language models. And this is why we are sort of trying to use common sense, but also include the axioms. So I didn't talk a lot about the psychological axioms of Gordon and Hobbes, but they tell us they complement knowledge graphs in a way that they add this sort of rule level where we know we have kind of additional higher level structures. For example, they tell us what does it mean for something to be substituted with another thing. So in that work, we have 3 different story types. We work with unmet expectations, we work with substitution, we work with, I don't remember the third one, but essentially the point would be that we kind of focus on this aspect of purpose when you kind of connect multiple events, and we can generate many stories. I mean, for now, the stories are honestly fairly simple, but we can generate a lot of them. And then kind of use those to improve the understanding of the models.
Thank you, Philip. Manuel, would you like to add anything?
So yes, our scripts are quite similar to what Philip described. So for us, they have to be multi-event multi-event complex procedures. They could be things as simple as baking a cake. More complicated, like purchasing a car or applying for a job. They can also be very large events that unfold over a long period of time, like a pandemic or an epidemic.
Thank you. So the next question is from Ron Brockman. This is for Philip. Your talk title mentions open world. So can you explain in a little more detail what you mean by open world? How that plays into the work you've talked about?
Yeah, thanks. So I kind of I mean, the talks are short, so I think this might have been indeed lost, and I appreciate you bringing this up again. So all of the work that we've been doing is zero shot or open world, in a sense that we never rely on the training data, and this is really the catch. So I think in our works we kind of start without assuming that there will be task specific training data to kind of help us solve the task. And this is inspired by the fact that we have seen that language models can learn very well to exploit the task-specific training data, as also I think both Xiang mentioned, I think also Ram mentioned this. But essentially doing this in a zero shot without relying on the training data forces you to build a generic model that can then operate in the open world and be able to solve a lot of different tasks. I talked about these different aspects. There is the naive physics, naive psychology, understanding common facts about the world. So in a sense, we want a model that can do all of this, a single model that can do all of these things.
Great, thank you, Philip. So any other questions for attendees? Please use the Q&A features. Let me see, there's another question from Bart Selman. Zhang, this is a question directed to Zhang. You noted how the current ML training test dataset paradigm leads to narrow AI. Commonsense error really concern out-of-distribution cases. How do we reach the out-of-distribution cases? Is there an alternative to the training test dataset approach?
Yeah, that's a great question. So our takes to this out-of-distribution generalization, I think has a couple aspects. One is like really learning about the logics and the reasoning process. For example, the primitive reasoning operations that you can do, and then really learning about how to compose these primitive reasoning actions into some more compositional and complex reasoning process. And in that process, you can also switch between different knowledge that you can using. For example, you can change the subject or the object for the reasoning primitive actions, but you can still get the similar process of drawing the conclusion. And in this way, if the model learn all these smaller steps, they will be able to do larger steps that are actually not well present in the training set. That's one way. Another way is to it's also along a more like a data-driven perspective, is trying to automatically perturb these like training data in the way that producing more phenomena that are not presented in training data, and such that the model can actually go beyond the training set distribution to do well. And of course, we can have human in the loop in this process to help us to navigate the model learning trajectory in a much more efficient way, rather than just let it randomly explore the vast rest of the data distribution space. So these are just like the two possible things we can do. Yeah.
Thanks, John. Moving on to the next question. This is directed toward Manuel. Manuel, this is a question from Teng Hao Huang. I'm wondering how well the model could capture the sequential knowledge. For example, in a baking scenario, steps would be to add powder, add water, bake. Bake would be the last step. Could the model capture this knowledge?
So yes, so we see quite often, and this is also our, one of our testing cases, baking a cake. We see that if the input to the language model is presented sequentially, so if we tell the model that the first step was to add powder and the second step was to add water, what would come next? We quite often see the model suggest baking the cake. What we cannot do right now is we cannot specify an event granularity. So we can't tell the model that we would like to say get the next step be something smaller, like preheating the oven. We also cannot tell the model that it should not jump to the end and just say enjoy your cake. But yes, sequence is captured as part of the input. So we always provide input in a sequence, so the model sees the steps as coming one after the other.
Thank you. So the next question, the last question, is from Xion Kim. This is directed toward Ram. What would be the state-of-the-art zero-shot image learning?
Sorry, could you repeat? What is the state-of-the-art in zero-shot learning?
Zero-shot image learning. Learning from images, yeah.
This is difficult to say. People are really not focusing very much on zero-shot. Even the non-zero-shot cases are low. Maybe a slightly broader perspective is that there's considerable work on few-shot learning. Like if you got one example or two examples or four examples, so you're not relying on language, but you're trying to generalize features. Zero-shot, there is very little work except for the clip model that I mentioned. And the question could be posed as, are there any zero-shot objects left after clip-like systems have been trained, because they have billions of images and is a minivan. In my example, I talked about a minivan or a moped not being seen, but clip would have seen them. So I think I'm not giving a satisfactory answer. There is relatively little work, and the state of the art is pretty weak. But in my funded projects, we are discussing about whether clip-like models don't solve these problems. And some people are opposed to using clip because they prevent us from exploring novel objects because there are no novel objects left.
Thank you. So work to be done. Thanks, Ram.
Yes.
So I'd like to thank all the speakers again, Philip, Manuel, Ram, and John, for this first session on common sense reasoning of the symposium. So this will conclude this session. There's a break, and then we look forward to having you all in the second session. Thank you again, and continue to participate in our symposium.